ठीक है. So today we will be going to discuss the fluidization. So what happens in fluidization? So when you are having a fluid flow through a porous media in a way that, let's say, you are having some bed. So it's a packed bed where you are having fluid is going through the bottom, and you are having a packed bed. So some fine particles are there initially. So this is the configuration at t is equals to 0, and fluid is not like fluid will go through it, and fluid is flowing through it. And what happens? So when the so at some later time, this will be the configuration where you are having a suspended, the particle will become suspended because of the fluid flow. So particle will go like this. So suspended in a fluid medium. So as the fluid is flowing, the particle will become suspended, and the process from going from the packed bed to the fluidized bed is fluidization. So basically, some fluid is flowing with some fine particle are there present inside uh, the uh, container, and so initially it has some length L, maybe at some initial height, that's the height of the packed bed, and after some time, they become that H will increase. So to understand fluidization, we should first plot uh, like how the this height of the packed bed is changing and how the pressure drop is changing. So for example, so I'm plotting two things, that is height, and I'm applying some, this is the superficial velocity through which it is the velocity of the fluid flowing through these particles. So this is the superficial velocity, and I'm plotting the how the pressure difference is changing across the length. Uh, how the pressure difference is changing. So this is the, so initially what happens when you are applying a pressure difference. So as you are increasing the velocity, there is a increase in the pressure drop across the bed. So across this bed, there is a pressure drop in between the here and here. So there is a constant increase in the pressure drop. But after some time, and height will, so there is a almost negligible change in the height till some pressure drop. But at some velocity, you will see a uh, you will see a change in height where, and this is happening because you are still applying the pressure and the velocity becomes so high that the pressure drop is high, and there is you will be able to see a change in the height of the bed, of the packed bed. And this is happening because it is just the gravity of the, like the net force on the particles, net gravitational force on the particle is balanced by the velocity, the force exerted by the fluid on the particles. Okay, so when you increase, so so this is also increasing, but this increase is comparatively lesser than this. So you will not see a significant change in the pressure drop after when we after certain V naught, and you will see a const like after this the packed bed, the height of the packed bed will increase as the pressure drop increases. So this is the point where this is the point where a pad become completely fluidized. Okay, so this is the point. So this is the velocity which we called as minimum fluidized velocity, minimum fluidization velocity. So this is the supervelocity velocity, and this is minimum fluidization velocity. Okay, so this is usually what is asked, that how to calculate this. Our objective is to know like how to calculate the minimum velocity required for fluidization, that is V naught m, minimum superficial velocity required for the, so that is minimum so the definition of the superficial velocity is, so basically velocity, we are not considering the effect of particle on the velocity. So superficial velocity is the V naught is the hypothetical velocity calculated as if a single phase I can say as if a fluid is, as if fluid is flowing without particles. ठीक है, so this is the superficial velocity. So this is the concept of fluidization, and we need to calculate this minimum fluidization velocity. इसमें कोई doubt?
No, sir. No, sir.
ठीक है, so The porosity of the packed bed can be written as it is the volume of the void divided by the total volume. So, so there are so in a packed bed there are voids. So this is the total volume. If you remove the particles, like the remove the volume of the particles, then that will give you that you will get the volume of the void. ठीक है. So at incipient fluidization. So incipient fluidization means when we are reaching to this state where the bed become fluidized. At that instant, the pressure drop applied across the packed bed should be balanced by the gravitational forces acting on the fluid particle. So delta P into cross-sectional area of this is the cross-sectional area. Delta P is the pressure drop applied into A should be equals to 1 minus epsilon. 1 minus epsilon is it will give you the volume of the 1 minus epsilon into total volume, that is A into L. So L is the length or at the incipient fluidization. So this is that L. uh, ठीक है. So I can say L at minimum fluidization. So this is L. So this is the total volume of the particles into density difference, that is rho particle minus rho F into G. So delta P by Lm, and this is epsilon m. So this is the porosity at incipient fluidization. At incipient fluidization. ठीक है. So this is 1 minus epsilon m into rho p minus rho f into g. So this is the equation we get by doing a, so the pressure force due to fluid flow is balanced by the gravitational force on the, ठीक है. So this is the equation. Now we wanted to, like, our objective is to know the V naught m, that is the velocity and minimum fluidization, and for that we have certain relation, that is delta P naught by L is given by 150 So at minimum fluidization 150 into V naught M to viscosity of fluid to 1 minus epsilon m divided by Vs, that is the porosity, dP square to epsilon cube. Sorry, Vs is the sphericity of the particle, which means that it will tell like how spherical the particle is, plus 1.75 rho. Rho is the density of the fluid, 1 minus epsilon m divided by Vs, and is the diameter of the particle into epsilon cube. And this is our Ergun equation. So using these two equations, we'll get, using 1 and 2, using equation 1 and 2, we can obtain the minimum fluidization velocity. Now, there are some points to note. Ergun equation is the combination of the, so this is my Blaise-Koszny equation. So this part is my Blaise-Koszny equation, and this part is my Burke-Plummer equation. Burke-Plummer equation. Okay. So here Vs is the sphericity of the particle, dP is the diameter of the particle. Rho F is the density of fluid. And mu F is the viscosity. Yeah. So this is it. And so there are certain conditions depending on the Reynolds number and the type of flow, which equation you have to use. Okay. So this we have to note. So uh, so I'm giving a table where Reynolds number of packed bed, and type of flow. The Reynolds number will tell whether the flow is in laminar regime or the turbulent regime. And the pressure drop, like the which equation we need to use for delta P by L. ठीक है, so when the Reynolds number of wet bed is less than 10, the fluid flow is essentially laminar, and the equation we use is Blaise-Koszny equation, and there is a reason behind that, like why the particular equation. When P is 10 to 2000, then it's a transition region, and we have to use the Erkan equation, which is the set of both Blaise-Koszny and Burke-Palmer equation. When Re is greater than 2000, then it's a turbulent flow, and we have to use the so usually you get the numerical where you will be asked to know to get the you need to calculate the fluid Reynolds number, and you have to choose the appropriate form of the equation to get the uh, minimum fluidization velocity. Okay, so Reynolds number of the packed bed can be written as rho f into dp. This velocity is the velocity of the fluid flow. It will be given to you, the superficial fluid velocity, and 1 minus epsilon into mu f. Okay, so this is the particle Reynolds number of the packed bed. Uh, this is this, and then so I'm saying why in laminar we have to use the Blaise-Koszny equation, and why in case of turbulent we essentially use Burke-Plummer equation. Because Blaise-Koszny equation is the artifact of Blaise-Koszny equation is essentially going to tell you the pressure drop due to the viscous loss. You will see viscosity is here, and Burke-Plummer equation and viscous forces are important at low REP, because at low REP you can see that REP become low when viscosity is significant. Okay, in case of Burke-Plummer equation, it's the kinetic energy. Kinetic energy loss, and you will see you will not see a viscous term here. And when you are at a very high Reynolds number, your viscous effects are almost negligible. So that is why we use Burke-Plummer equation at high REP, because you can see that at high REP, viscous effects this become high when inertial term, the inertial forces are significant compared to viscous terms. and then kinetic energy losses are significant. So, so in GATE, there was one question in 2011. So the question is, अभी तक किसी को कोई डाउट है?
नो सर।
क्या हुआ? हंसी क्यों आ रही? कोई डाउट है तो पूछ लो.
नो सर।
हाँ, कोई डाउट नहीं है. This equation is valid when, like, I can say that this may not needed to be like always you wanted to get the. So you using this equation, you will get the pressure drop in general. But if you wanted to know the minimum fluidization velocity, you need to use equation 2 and equation 1, and then epsilon becomes epsilon m. So it is not always the case that epsilon will epsilon m. So it is in general. Okay. So the question is, the data is given as like that. Yeah, gate 2011 and use the following data to answer these questions. So we are having a for the fact that, so you are having the diameter of the particle that is 10 to the minus 3 meter. Then you have sphericity of the particle that is 0.8. Then you have density of the fluid which is 1000. Then you have the viscosity of the fluid that is minus 3 kg per meter second. Then you have the density of the fluid particle that is kg per meter cube, and g you can take 9.8 meter per second square. So first question is, when v naught, the superficial velocity, is 0.005 meter per second, and epsilon, so at this velocity epsilon is given to be 0.5, which one which one of the following is the correct value for the ratio of viscous ratio of pressure drop due ratio of viscous law to that of kinetic energy loss. Options are 0.09, 1.07, 10.71, 93. Another part is on further increasing V naught, incipient fluidization is achieved. Assuming that the porosity of the bed, assuming that the porosity of the bed remains unaltered. The pressure drop per unit at the pressure drop per unit length under incipient fluidized bed condition is, options are ठीक है. So this is the question. करो फिर सॉल्व, उसके बाद मैं बताता हूँ आंसर. ट्राई करोगे? हेलो,
Yes, sir.
करो फिर ट्राई. टू विस्कस लॉस क्या है तुम्हारा? ये है ना 150 वी नॉट म्यू एफ. वी नॉट म्यू एफ into 1 minus epsilon square divided by Vs square dp square into epsilon cube. और काइनेटिक एनर्जी लॉस क्या है? 1.75 v naught square to rho into 1 minus epsilon divided by Vs into dp into epsilon cube. यही है ना आपने को चाहिए? विस्कस लॉस थ्रू दैट काइनेटिक एनर्जी लॉस. ठीक है, यही है ना, यही क्वेश्चन यूज किया हो ना. हेलो.
Yes, sir.
1.75 v naught square rho f 1 minus epsilon into Vs into dp into epsilon cube. इससे ये गया एक वी नॉट से, एक वी नॉट गया, एक वी एस से एक वी एस गया, एक डीपी से एक डीपी गया. तो क्या है अपने पास? 150 डिवाइड बाय 1.75 into mu f to 1 minus epsilon divided by Vs into dp, Vs into dp into v naught. ठीक है, so 150 divided by 1.75 तो mu f क्या है? mu f है 10⁻³ 1 माइनस एप्सिलॉन क्या है? 0.5 डिवाइड बाय Vs क्या है? 0.8 इंटू पार्टिकल का डायमीटर क्या है? 10⁻³ इंटू वी नॉट क्या है? 0.005। इससे ये गया, क्या बचा तुम्हारे पास? इसका ये हो गया 0.5। ठीक है, तो ये 1010, ये बचा 100। क्या है तुम्हारा? 15, एक और 0, 1.75। डेंसिटी, आई थिंक आई फॉरगॉट डेंसिटी। यहाँ पे रो एफ भी आएगा ना, रो एफ। तो एक 10⁻³ यहाँ पे आएगा, इससे ही गया। तो ये आया 150 डिवाइड बाय 8 इंटू 1.75। कैलकुलेट कर लो। तुम लोगों ने क्या गलती करी थी?
सो फॉर्मूले में गलती कर दी थी। यहाँ पे जो नीचे इसमें डिस्कस लॉस में दे रखा ना नीचे वाला, उसमें वो क्यू दे रखा था, और इधर स्क्वायर, तो स्क्वायर नहीं लगा था, डीपी स्क्वायर, वो पूरा पूरा काट दे रहे थे।
ध्यान से करो भाई, न्यूमेरिकल। तो ये आंसर है। सेकंड वाला पार्ट किया? हाँ।
सभी कर रहे थे, फॉर्मूला पुट करना चाहिए था उसमें।
हाँ, ये तो स्ट्रेट फॉरवर्ड ही है, मतलब डेल्टा पी बाय एल, मिनिमम फ्लूइडाइजेशन पे प्रेशर पर यूनिट लेंथ निकालना है। तो जी इंटू रो पी माइनस रो एफ इंटू 1 माइनस एप्सिलॉन। So that is 9.8 into 1000 into 2500 minus 1000, and this is 0.5। तो ये तुम्हारा आएगा 7350 पास्कल। So this is it। ठीक है।
यस